Okay, hi everyone. This is Math 22A Quiz 3 key. Okay, so the first problem here says I started with the matrix A. I did row operations to A and found that a bunch of these elementary matrices times A ended up in this upper triangular matrix. Find the determinant of the original matrix A. You may leave your final answer as a product or quotient of integers. So show your work. Okay, so the idea here is that we know if I name these matrices, so I'm going to name them E1. This is the first elementary row operation that we applied to A, and then E2, E3, E4, E5, E6. So E6 times E5 times E4 times E3 times E2 times E1 times A is equal to, and I'm going to call this one D. Okay, so it's I'm sorry, not D. I'm going to call it U, an upper triangular matrix. Okay, so what we have is then that since these two matrices are equal, this product is equal to U, we get that the determinant of E6 times E5 times E4 times E3 times E2 times E1 times A is equal to the determinant of the upper triangular matrix U. Now, we know that the determinant of a product of matrices is the product of the determinant of the matrices. So we know that this is the determinant of E6 times the determinant of E5 times the determinant of E4 times the determinant of E3 times the determinant E2 determinant E1 times the determinant of A, which is what we want to find to begin with. So we have the product of all these determinants is equal to the determinant of U. Okay, now the determinant of U, since this is an upper triangular matrix, is just the product of the entries on the diagonal. So this is 2 times 6 times 9 times 11. Now we know that the determinant of E6, so E6 here is just a matrix that adds a multiple of row 2 to row 3. Okay, so the determinant of that matrix is 1. If you remember back to the first day we talked about determinants, we figured out that the determinant of an elementary row matrix which adds a multiple of one row to another was just 1. The same thing happens here. The determinant of E5 is 1 because E5 just adds 3 copies of row 3 to row 2. Okay, now E4, it scales one of the rows. It takes the first row and multiplies it by 7, so the determinant of that matrix is 7. It's also just the product of the entries on the diagonal. Now E3 is a permutation matrix. It swaps 2 of the rows. So notice it takes row 3 and puts it in row 2 and takes row 2 and puts it in row 3. Now it's just swapping 2 rows. One swap means that the determinant of E3 is just -1. Now E2 is also a scaling matrix. So the product of the diagonals is 5. That's the determinant. Now the determinant of E1 is, now this is also a permutation matrix. It swaps rows 3 and rows 1. So it takes row 3 and puts it in row 1, takes row 1 and puts it in row 3. So the determinant of that matrix is -1. So then what we find is that the determinant of E6, which is 1, times the determinant of E5, which is also 1, times the determinant of E4, which is 7, times the determinant of E3, which is -1, times the determinant of E2, which is 5, times the determinant of E1, which is -1, times the determinant of A is equal to the determinant of U, which is 2 times 6 times 9 times 11. Okay, so there's only one thing we're looking for here, that's the determinant of A. So we get that the determinant of A is 2 times 6 times 9 times 11 over 35, right? 5 times 7 Those negatives cancel when we divide. Okay, so the second problem asks us to find the determinant of each matrix using any method. Okay, so this first problem, there's a couple of ways to do it. We can either realize that this matrix is really a diagonal matrix with just a bunch of row swaps and figure out, first of all, what the product of the diagonal matrix would be, and then calculate the proper row swaps that are required to then compute the total determinant. Or we can just use cofactor expansion. So let's just use cofactor expansion for the practice. So let's look for a row that has a lot of zeros. Well, look, yes, all of the rows have a lot of zeros. The first row has only one non-zero entry, so let's expand about that. So the determinant of this matrix is 2. So we take this 2. Now we're going to take -1 to the 1 plus 5. This is the I equals 1, j equals 5 entry. So we get -1 to the 1 plus 5 times the determinant of this submatrix, which is given by these first four columns minus the first row plus the last column minus the first row. Okay, so I'm just going to write that down. So 3, 1, 2, 3, 4, 0, 4, 0, 0, 0, 0, 0, 0, 0, 5, 0, 0, 0, 6, 0, and then 0, 0, 7, 0, 0. Okay, cool. So now let's do the same thing here. We'll expand around this first row. So we get 2 times -1 to the 1 plus 5 times 3 times -1 to the 1 plus 1 times the determinant of this smaller matrix, 4, 0, 0, 0, 0, 0, 0, 5, 0, 0, 6, 0, and then 0, 7, 0, 0. Okay, which then is equal to, now let's do the same thing again. We'll expand around the first row. So we get 2 times -1 to the 1 plus 5 times 3 times -1 to the 1 plus 1 times 4 times -1 to the 1 plus 1 times the determinant of this smaller matrix, 0, 0, 5, 0, 6, 0, 7, 0, 0. Okay, we're almost done. Now we get 2 times -1 to the 1 plus 5 times 3 times -1 to the 1 plus 1 times 4 times -1 to the 1 plus 1. Okay, now let's expand around this first row again. So we're going to get times 5 times -1 to the 1 plus 3 times, now we just have a 2 by 2 subdeterminant. We have this 0, 0, 6, 7. So we're going to have 0 times 0 minus 6 times 7. Okay, so now let's just work this all out. This is -1 to the 1 plus 5 is -1 to the 6, which is 1. -1 to the 2 is also 1. -1 to the 2 is 1. -1 to the 4 is 1. So these are all positive. This is the only negative. So we get -2 times 3 times 4 times 5 times 6 times 7. That's our answer. Okay. Now this second one, we could do cofactor expansion. Now here I'm going to choose to use row reduction and keep track of the changes to the determinant. And I'm choosing to do that because I'm noticing that while this is a matrix that has a lot of zeros that we can maybe expand around, there's a lot of numbers. There's sort of like a lot of places where the numbers aren't going to maybe reduce as easily as I would want them to. So yeah, so okay, so the first thing I'm going to do, I'm going to do some row reduction, and I'm going to keep track on top of these like row reduction steps what happens to the determinant. So if I multiply something by 5, then I'm going to keep track of the fact that I multiplied my determinant by 5. And when I go on, if I multiply my determinant by -1, or do something where I have to do that, I'm going to keep track with a times -1. So the first thing I'm going to do is swap these first two rows. Okay, when I do that, I get 1, 1, 2, 3, 4, 2. Okay, I'm swapping this row with this second row, or sorry, this first row. 2, 1, 2, 0, 0, 2. And the rest of them are going to stay the same. 5, 6, 7, 1, 8, 9, 3, 4, 0, 0, 7, 2, 4, 0, 1, 0, 0, 1, 5, 0, 2, 0, 0, 3. Okay, so in swapping those two rows, I changed the determinant of this matrix. This matrix has determinant -1 times the determinant of this matrix. So I multiplied times -1. Okay, now I'm going to use this first row to zero out all of the entries below. Okay. Now one thing to kind of keep track of is, even though I'm doing more than one step here, because I'm doing all steps that are the same, it doesn't matter, and I just need to keep track of how the determinant changes for those steps. So all of those steps, since I'm going to be taking these rows and adding multiples of this first row to it, all of those are going to be not changing the determinant. So I have times 1. Okay, so here I swap the sign. Here I'm not actually changing the sign at all. Okay, so this first row stays the same. Now I'm going to take each of these rows and subtract the appropriate multiple of the first row. So the second row minus 2 times the first row is 0, 1, 2, 0, 0, -2. Okay, now this third row minus 5 times the first row is 0, 6, 7, 1, 8, 9 minus 10 is -1. Okay, now this fourth row minus 3 times the first row, 0, 4, 0, 0, 7. Okay, and then 2 minus 6 is -4. Okay, now the fifth row minus 4 times the first row, 0, 0, 1, 0, 0. Now 1 minus 8 is -7. Okay, now the next row, I'm going to have the sixth row minus 5 times the first row, which is 0, 2, 0, 0. Now 3 minus 10 is -7. Okay, and in going from this matrix to this matrix, I didn't change the determinant at all. Okay, so another step now. So now I'm going to use this second row, 1, 2, 0, 0, -2, to zero out these two rows below it. Okay. And notice too that I'm going to be just adding a multiple of the second row to the third and the fourth rows. So that's not going to change the determinant at all. So this is times 1. Okay, so the first row unchanged. 2, 0. The second row is also unchanged. Okay, now I'm going to take the third row and I'm going to subtract 6 times the first row. So I get 0, 0. 7 minus 12 is -5, I believe. Yes, -5. And then 1 minus 0 is 1. 8 minus 0 is 8. And then -1 minus -6 times -2 is 12. So -1 plus 12 is 11. Okay, now I'm going to take the fourth row and subtract 4 times the second row. So I get 0, 0, subtract 4, negative 8, 0, and then 7, and then negative 4 plus 8 is 4. And these next ones are unchanged. 0, 0, 1, 0, 0, negative 7, 0, 0, 2, 0, 0, negative 7. Okay, so now I'm going to use a row swap, and I'm going to move this 5th row up into the 3rd row spot. So I'm going to swap row 5 and row 3, which is going to change my determinant, change the sign of my determinant. So I get 1, 0, 0, 0, 0, 2, 0, 1, 2, 0, 0, negative 2, 0, 0, 1, 0, 0, negative 7, and then 0, 0, negative 8, 0, 7, 4, and then the 5th row, which is now the 3rd row, 0, 0, negative 5, 1, 8, 11, and then finally 0, 0, 2, 0, 0, negative 7. Okay, so a couple more steps. So now let's use this 1 here to zero out the entries below it, which we know is just going to keep the determinant the same. So we're going to take this row 4 and add 8 times row 3. Okay, so negative 8 plus 8 is 0, 0, 7, now 4 plus 8 times negative 7, which is negative 56, we get negative 52. Now we're going to take this row 5 plus 5 times row 3, which is 0, 0, 0, 1, 8. Now 11 minus 35 is negative 24. And then now we're going to take this row and subtract 2 times row 3. So row 6 minus 2 row 3 is 0, 0, 0, 0, 0, negative 7. Okay. Oh, sorry, positive 7, not negative 7, positive 7. Okay, one last step. So notice we're almost to an upper triangular matrix. We just need to swap rows 5 and 4. One row swap changes the sign of the determinant. So 1, 0, 0, 0, 0, 2, 0, 1, 2, 0, 0, negative 2, 0, 0, 1, 0, 0, negative 7, 0, 0, 0, 1, 8, negative 24, 0, 0, 0, 0, 7, negative 52, 0, 0, 0, 0, 0, 0, 7. Okay. Whew, we're done. So now we just want to check the determinant of this matrix. So it's an upper triangular matrix. So to get the determinant, we just take the product of the entries on the diagonal, which is 1 times 1 times 1 times 1 times 7 times 7, which is 49. Okay, now let's work backwards and see what the determinant of this matrix was. So the determinant of this matrix was 49. So the determinant of this matrix must have been minus 49, since minus 49 times negative 1 is 49. So then that means that this matrix has determinant negative 49. It's unchanged here. Swap signs here, we get determinant 49. No change here, still 49. No change here, still 49. And then a minus sign, we get minus 49. Okay, so the determinant of this original matrix, when we walked back through all the steps, must have been negative 49. Okay. So problem 3 reads, each set below is a subset of R5. Determine whether each is a subspace of R5 and explain your reasoning. Okay, so we need to check to see if it satisfies additive and multiplicative closure. So the two things we're going to do, for additive closure, we're going to take two arbitrary vectors in this set. We're just going to figure out what that means that they're in the set. And then we're going to see if that means that the sum of those two vectors is also in the set. Okay, so additive closure. We're going to take two elements of this set, so A1, B1, C1, D1, E1, and A2, B2, C2, D2, E2 are in V. Okay, so we're taking two elements of the set, and that tells us, since they're in the set is all of the vectors where twice times the first component plus the last component is equal to 0. So twice times the first component of this vector, 2A1, plus the last component, E1, must be equal to 0. And the same for this vector. Twice times the first component, A2, plus the last component, E2, is equal to 0. Okay, so we take two vectors in our set. We know something about their components. Then we want to add together the vectors. So A1, B1, C1, D1, E1, plus A2, B2, C2, D2, E2 is equal to A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, and E1 plus E2. Okay, now we want to check to see if this is in the set. And it is in the set. We need to check why. So we want to take twice times the first component plus the last component and see if we can simplify this until we know that it's 0, meaning that this vector is then in the set. So if this vector has twice times the first component plus the last component is equal to 0, we know that that's in the set and it will satisfy additive closure. Okay, so 2 times A1 plus A2, this is the same, I'm just going to reorder things, 2 times A1 plus E1 plus 2 times A2 plus E2. Now those are exactly the equations that we got from the first, the vectors being in the set V. So we know that 2 times A1 plus E1 is 0 and 2 times A2 plus E2 is 0, which means that together this is all 0. So this does satisfy additive closure. And I'm going to put in words. So this says if I take two vectors in my set, using what I know about them, then I know that their sum is in the set because when we use these two equations which describe their components, we get the same equation for the components of the vector, which is the sum. Okay, so now let's take multiplicative closure. Okay, so we take a vector in our set, A1, B1, C1, D1, E1 in V. So 2 times A1 plus E1 is equal to 0. And then we're going to look at a constant multiple alpha times A, B, C, D, E1s. Okay. This is in the set V, and we just need to check that this vector satisfies this equation. Okay, so twice times the first component. So the twice times the first component is 2 alpha A1, multiplying the alpha in, plus the last component, which is alpha times E1. Now I'm going to factor out alpha, 2A1 plus E1. Well, 2 times A1 plus E1 is 0 since this vector we chose was in V, so it satisfies 2A1 plus E1 equals 0. So twice times the first component plus the last component is 0. So we get that this is really just alpha times 0, which is still 0. So it does satisfy multiplicative closure. So then we know this is a subspace. Okay. Okay, the second set is the set where the product of the first and last components is 0. So all the 5 vectors where the first component times the last component is 0. Now this isn't going to be a subspace. So one way you can kind of get some intuition for whether or not something is going to be a subspace is just start trying to write out what it would mean. So, you take 2 vectors whose product of their first and last components is 0, and then when you add them together, see what the product of the first and last component is. Is it something that's going to simplify to use only the equations you already know from the descriptions of your vectors in your set? Or is it something that you can't guarantee to be 0? Then once you have that intuition for whether or not something is a subspace, if it's not a subspace, if you think it's not a subspace, then try to come up with a counterexample using the information you just figured out. Okay, so this isn't a subspace. So for example, if the first and last components of our vector are 0, we know one of them must be 0. So let's choose first just a vector where the first component is 0, and let's just call all of the rest of them 1s. That could be literally anything. Now let's take another vector where the last component is 0. Okay. So both of these are in W, but then let's look at their sum. So the sum is 1, 2, 2, 2, 1, which is not in W, since the product of the first and the last components is not 0. So this is not a subspace. Okay, the fourth problem asks us to determine whether the vector 1, 2, 3, 4, 5 is in each subspace of R5. Okay, so first of all, remember that the span of these 3 vectors is really just the set of all linear combinations of them. So C1 times the first vector plus C2 times the second vector plus C3 times the third vector. Okay, so this is exactly the span. The span is just the set of all linear combinations of the vectors. Okay, so if we want to show that this is in the span, we just really want to show that this is in this set of linear combinations. Or in other words, we can find coefficients so that whatever your particular C1 times the first vector plus C2 particular C2 times the second vector plus your particular C3 times the third vector is equal to this, this vector. Okay, so in other words, we want to solve the system of equations 1, 2, 3, 4, 5. So the vector, we want to show it's in the span. So we want to show that there are coefficients that satisfy this equation. Okay, so this is just a system of equations, something we've been solving for several weeks now. So we're solving for C1, C2, C3, so let's write our augmented matrix. Okay, so 1, 0, 1, 0, 2, 1, 2, 0, 2, 1, 0, 6, 0, 8, 1. And then we want to get 1, 2, 3, 4, 5. Okay, so let's go ahead and solve. Okay, so let's use this first row to zero out the rows below it. So 1, 1, 0, 1. The second one, it's already got a 0 below the diagonal. Okay, let's use this one to zero out this one. So row 3 minus row 1 is 0, -1, 0, 3 minus 1 is 2. The fourth row already has a 0. And then we're going to take row 5 minus 2 times row 1, which is 0, negative 1, 1, and 3. Okay, so now let's swap rows 3 and 2 and multiply row 3 at the same time by negative 1. So 2 steps, taking row 3, swapping the signs, and then I'm swapping this row with row 2. So 1, 1, 0, 1. Now we're taking row 3, getting rid of the negative sign, so we get 0, 1, 0, negative 2. And then 0, 2, 6, 2, 0, 2, 8, 4, 0, negative 1, 1, 3. Okay, now let's use this 1 to zero out these entries here. So we get 1, oh, and let's also zero out this entry. So we're going to take row 1 minus row 2. So we get 1, 0, 0, row 1 minus row 2, so 3. Row 2 is okay. Okay, now row 3 minus 2 times row 2. 6. Okay, and then 0. We're going to take row 4 minus 2 times row 2. 4 minus negative 2 times negative 2. Or sorry, minus negative 2, which is, or 2 times negative 2, which is negative 4. So this is 4 plus 4, which is 8. And then we're just going to add row 2 to row 5. So 0, 0, 1, 3 minus 2, which is 1. Okay, so this is really nice. Notice this is just the row 1, 1, the row 1, 1, row 1, 1, right? So these are all the same 3 rows. We would divide each one by 6, 8, and 1. So this goes to 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, now notice we're just going to use this row to zero out these 2 rows. So the 1, 1 we'll get rid of these, and we'll just end up with 2 rows of zeros. So this row is 1, this is negative 2, and this is 3. Okay, so this tells us that our coefficients are 3, negative 2, and 1. So in other words, I want to check that when I multiply the first vector by 3, the second vector by negative 2, and the third vector by 1, that I get 1, 2, 3, 4, 5. Okay, so let's check. This is 3 times 1, 0, 1, 0, 2, plus negative 2 times 1, 2, 0, 2, 1, plus 1 times 0, 6, 0, 8, 1. Okay, so let's check what we get in each component. So we're going to get 3 times 1 minus 2 times 1 plus 0 is 1. 3 times 0 minus 4 plus 6 is 2. 3 is just 3. Now 0 minus 4 plus 8 is 4. 6 minus 2 is 4, plus 1 is 5, and we do get that these are equal. So we just checked our answer. Our answer is a set of coefficients that show that this vector is in the span of these 3 vectors. So yes, it is. Okay, now let's look at this set of vectors and see if 1, 2, 3, 4, 5 is in the span of these 4 vectors. So again, we get the same exact sort of situation. We're going to set up our augmented matrix. So 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and then we get 1, 2, 3, 4, 5. So right away I know that this isn't going to work. So notice I look at my rows, and I have two rows that on the left-hand side have 0, 1, 1, 0, but then on the right-hand side I have different values. So this is going to give me a contradiction. So this is no solution. So no solution meaning no coefficients, so that this vector is a linear combination of these vectors with those coefficients. There are no coefficients that exist for that, which means it is not in the span. So part A, yes, it was in the span. Part B, it was not in the span. Okay, now finally, problem 5. Below are 3 sets of vectors in R5. Determine whether each set is linearly dependent or linearly independent. Show your work or explain your reasoning. Okay. So what do we want to see here? So to see whether something is linearly independent, we have to check to see if there's a set of coefficients that when we take the linear combination of these vectors with those coefficients, if it gives us 0, and then we need to look at those coefficients and see if they're all 0 or not 0. So if they're all 0, if the only way to sum a linear combination of these vectors is to use coefficients that are 0 to get 0, then it's a linearly independent set. If there is a non-zero coefficient on one of these, then that means the set is actually linearly dependent. Okay, so we're really just solving C1 times 1, 0, 0, 0, 1 times these vectors. Is equal to 0. Okay, so we want to see what the coefficients are that give us, that satisfy this system of equations. And then we want to check those coefficients and see if they're all 0 or if any of them is non-zero. If any of them is non-zero, then that means that we have linearly dependent. So non-zero coefficient. And if it's linearly independent, the only solution will have 0 coefficients. Okay, so let's set up our augmented matrix. So 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay, cool. So let's do one step of row reduction. So notice if we take row 5 and we subtract row 1 and we subtract row 2 and we subtract row 3 and we subtract row 4, we get rid of all of these entries right here. So what we end up with is 1, okay, so I took row 5 and I subtracted row 1 and row 2 and row 3 and row 4. And notice I get a diagonal matrix here, and it tells me that C1 equals 0, C2 equals 0, C3 equals 0, and C4 equals 0, right? So we take these first 4 entries, those are our solutions. This one is just telling us that one of the equations was redundant. Okay, now the second one, we want to see if there's a set of coefficients so that when we take these vectors and we add them all together, we get 0. Okay, so one thing to notice is we have a 1 here in the first component, second component, third component, fifth component, and we have zeros all the way through in the fourth component. So right away I can see that if I take 5 times the first vector, oops, that's too many zeros, plus 4 times this second vector, plus 3 times the third vector, plus 2 times the fourth vector, minus this vector, I get all zeros. Okay, so I just saw, oh look, these look like nice standard basis vectors, and the only one we're missing doesn't really matter because there's a 0 here. So I quickly figure out the linear combination that sums up to 0. Now notice there are non-zero coefficients here that satisfy a linear combination of our set of vectors is equal to 0. So that tells us no, these are linearly dependent. Okay, so any non-zero coefficients existing tell us that these are linearly dependent. Since these were all 0 coefficients, these are linearly independent. Okay, so now we want to see what coefficient times this vector is equal to the all zeros vector. Well, notice that's only true if c equals 0, which tells us that this one vector is linearly independent. Okay.